Last time we were working in section 11.4, which is the cross product, and we had gotten through with our properties. So we had algebraic properties, we had some geometric properties, and we are going to do an example next that involves those properties. So example number 2. We're going to find the cross product of u and v, and we're going to then show, we've claimed this to be true, but we're going to show that what we've found really is orthogonal to u and v. So, vector u is -1, 1, 2. Vector v is 0, 1, 0. And we did cross products last time, but it's been a couple days. And if you'll remember, the way that I showed you how to set them up was in terms of, so I didn't write that right, was in terms of expanding along determinants. And so, actually, you know what? I think I will. I'll show it as the determinate form just to remind you where it all comes from, since this is the first one we've done today. IJK, and we put u across the middle, so that's -1, 1, 2, and then v, which is 0, 1, 0. If you don't need to see it, don't write that down, and then we're going to expand along the top row. So we have I times 1, 2, 1, 0. Remember, it's the rows and columns that I is not on that you use. We do minus j. Rows and columns that j is not on would be -1, 2, 0, 0, plus k, and the rows k is not on are -1, 1, 0, 1. All right, so let's see, part of I is 0, that piece, and so then I have minus 2i, so -2. I'll write it in IJK form. So -2i, and then minus j, and j actually ends up being 0 along both diagonals when we multiply. So the j is 0j. You can write 0j if you want, or just leave it out. And then on k, we get this diagonal where it's going to actually have value. The other diagonal's value is 0. So that would be -1k, or -k. And IJKs have hats on them if you want to be pretty clear. If you want to write that in component form, that looks like -2, 0, -1. And we'd like to show that that is actually orthogonal to u, which is, in a separate step, we'll do orthogonal to v. So how did we decide, or what did we know made us, well, what condition must be met if we actually have orthogonal vectors?
Where did -2i come from?
Right here, 2 times 1.
Oh, yeah, actually it's
Yep.
subtracted.
Yeah, so it was a subtraction step from the determinant.
It's if you take a dot product of u and v, that equals 0.
Right, the dot product of whatever we're trying to decide between, right, is going to be 0. And we're trying to say that what we just found in u cross v is going to be orthogonal to u. So we want the dot product with u. And I'll do the same thing in a moment and do the dot product of that with v. So for the u cross v, I had -2, 0, -1. And u itself was -1, 1, 2. And of course, dot product, you just turn in homework for that, right, is a scalar multiple. So you have -2 times -1 plus 0 times 1 plus -1 times 2. What do we get? 0. And we'll do the dot product as well with v. So u cross v dot v. So I have -2, 0, -1. And I want to do a dot product of that with v. And v is 0, 1, 0. which is fabulous because there's a 0 in either one or the other of each of these vectors components. So I end up getting negative 2 times 0 plus 0 times 1 plus negative 1 times 0 for, of course, a 0. Okay. And it's not like it was a question. It didn't say, are they orthogonal? We know that they are. That's what we are finding when we're finding the cross product, is we're finding the orthogonal vector. We're just showing that it's true, right? We're showing that it's actually going to hold. Any questions on that? All right, for example number 3, we're going to look back at a unit vector. So we're going to find a unit vector orthogonal to U and V. So what is this asking us to do? Don't just restate the question for me. What are we literally going to compute? Okay, so we're literally going to compute the cross product, right? And the cross product will give us an orthogonal vector. And then,
we need to take the magnitude of that.
right. Then we're going to need the magnitude of that, and we're going to have to divide by it. Right? That's how we find unit vectors, is we divide by the vector's magnitude. So we're going to find U cross V. Oops, I didn't write down U and V yet. My bad. Move that down. So U is 3I minus J, and V is 4J plus K. And for this one, I'm going to go ahead and just do the expansion without writing out the original 3x3 determinant, but if you need to see it, please do use it. So this would be negative 1, 0, 4, 1, minus J, which is 3, 0, 0, 1, plus K, which is 3, negative 1, 0, 4. So this diagonal gives me negative 1, so that's negative I. This diagonal gives me 3, so I've got negative 3J. And then this diagonal has me at 12, so I have 12K. That's my orthogonal vector, and then Ethan said I needed to find the magnitude, right?
Do they all have hats?
They do have hats, yeah. Every time I write IJK, they should all have hats. Yes, they should. And then we're going to find the magnitude of what we just found, so the magnitude of U cross V. So that's the square root of each of the components squared. So I don't really need the negatives. Are you guys okay with me not writing negatives down for squaring things? All right, good. I have 1 squared plus 3 squared plus 12 squared. What is that a total of? 154 underneath the radical. So what's my unit vector? Yeah, so 154 unfortunately doesn't simplify in radical form, and when we divide by it, now we have radicals in denominators, so we have to rationalize. This is what it ends up giving us.
Wait, can't you simplify it by taking out 4?
What is it if I divide by 4? Well, is it divisible by 4? I don't think so. It's divisible by 2, but I don't think it's divisible by 4.
It is.
It is?
150 is divided by 4. Gotcha, 1 second, hold on. You're right.
Is it? Okay.
Because you have 120 plus 34.
Somebody just decide. It's not. It's like, I don't think so. The divisibility test, the divisibility test for deciding if something's divisible by 4 is that the last 2 digits as a whole number have to be divisible by 4, and 54 is not divisible by 4. So that one doesn't work. I can reduce at the end the 12 over 154, so we could do that. I just noticed that. These are both even, right? So 12 would be 6
6 over
And-
77.
77. Almost kind of would rather leave it as 154, just visually speaking, because they all have 154s, but we could reduce it. Okay, any questions on that one? Becca? Like on that one, to leave it over the 154, that's fine with me. I don't care on that. Yeah. WebAssign might not allow you to put it in that way, just thinking about that. I almost think it would fuss at you. Yeah. It doesn't make you simplify with radicals? Good to know. Okay, one more example and we'll be done with cross products, or at least the lesson for cross products. Number 4. We're going to find the area of the parallelogram that has the given vectors as adjacent sides. Vector u is ijk. And vector v is jk. And before we do anything, yours is probably still on your same piece of paper. It's not on my same screen, so I'm going to switch back my screens and we're going to revisit what we wrote down at the very end last time about geometric properties. We talked about several, we didn't really talk too much about them, we just wrote them down, several geometric properties of cross products, and the fourth one on here is the one that's valuable to us. It actually tells us that the magnitude of the cross product is the area of the parallelogram with adjacent sides u and v. So we can use that. So really all we're calculating on this one is u cross v and its magnitude.
We're dealing with ones.
And they're all ones. There's a whole bunch of ones everywhere. So nice, right? Okay, so if I'm looking at magnitude, if I'm looking at cross products, u cross v, they are all ones, but one of them also has a 0 in it, right? Yeah, so be aware of that. So we have I, and then we have 1. Hang on, I'm on the wrong page of my notes now that I switched back. Move back where it was. Here we go. 1, 1, and 1, 1, and then minus j, which is 1, 1, 0, 1, and then plus k, and then that matrix is 1, 1, 0, 1 as well. Right, and so I end up getting 0 here, right? Because the diagonals are matching. So we'll just write it in component form this time, just so that we can have another version. On this one, I have 1 times 1, and that one's non-zero, so I have negative j or negative 1
Wait,
j.
this is 0.
What's 0?
Never mind, sorry.
Okay, that's all right. And the same thing will happen for k. I've got this diagonal equaling 1, but of course the k coefficient is positive, so this is a positive 1. Okay? Yeah.
Scale.
If I did get a 0 vector here, we would have problems, right? Like we would have no area and so forth because there'd be no magnitude, but which would mean the parallelogram doesn't exist. That's what that would actually mean. But we don't, and so we can do our magnitude here. Not a very exciting magnitude, granted, but I have 0 squared, 1 squared, and 1 squared. So what's the area of this parallelogram? Square root of 2.
Do we have units?
No, because we weren't given units to start with. Yeah, if we had units to begin with, we would have units at the end as well. An area would be square units. Yeah. Okay, homework for this section. Page 781. Numbers 7, 10, 11, 14, 18, 19, 21, 24.